All right, so we write rate laws like this, and what we were doing the long way was comparing two different experiments or mixtures or whatever they were, where they did a reaction one time, and then they started over and did a reaction a different time, um, and we did the long way. Now, again, the overall point of this is to figure out what these exponents are. So before we did this, we did mechanisms to write rate laws, and it was in terms of what we're doing now and what we were doing then, this is a lot more work. Mechanisms are pretty easy. You find the slow step because it tells you, and you just write a rate law based on it. This is a little bit more labor intensive. And then I showed you last time a way to do this by inspection, which I kind of called this shortcut method. So let's reiterate, and I want to just kind of review that again. So again, what you do is you go, okay, this is my general rate law. So I go, okay, if I want to know the order with respect to x, I'm going to, for right now, just focus on x. So I'm going to see how x changes, and hopefully y is not changing. So that will help us focus on just how x is changing the rate if y is not changing. So look at, between experiments 1 and 2, the concentration of x doubles. Here to here is a double. Y is not changing, so I can ignore it. And the rate is doing what? Quadrupling, right? 1 to 4 is a quadruple. So the rate is quadrupling. The concentration of X is doubling. So what does M have to be? It has to be a 2, right? 2 squared is 4. That means it is second order. Oh my goodness. With respect to X. So basically, this guy is a 2. Okay? And then we do it again, but we do it for Y. And again, we're doing this like little shortcut way where we're not writing every single thing out. We're kind of just doing it by what's called inspection. So if we want to look at Y, we go, okay, well, for Y, we would like X to not be changing because that will help us hold it constant. So between experiments 1 and 3 or 3 and 1, it doesn't matter who's on the top or who's on the bottom. It just depends on if you want to think of them in terms of fractions or whole numbers, really. So I noticed in experiment 1 and 3, X is not changing. So that's great because Y is changing between experiments 1 and 3. Now, so I'm going to look at it a specific way because it's going to make my life easier. So from 0.0125 to 0.025, the concentration of Y is doubling. Is that right? Okay. The concentration of Y is doubling. I don't know its order yet. What is the rate doing? So if you're looking conceptually from here to here, you also have to go the same way, here to here. Well, 1 to 1 is like doing nothing. It's not changing, so that number is 1. So 2 to the what is 1? Well, this is 0, right? Anything to the 0 power is 1. So it is 0 order with respect to Y. Again, this is done by inspection as opposed to like writing out a rate law for 1, a rate law for 2, doing all of that math. However, it gets the same outcome. Okay, that's why they kind of call this a shortcut. Now, I wanted to tell you that when they ask you on the AP test or my test to write rate laws, you probably could do this without showing any work because it's fairly easy to inspect. However, even if you don't do it the long way, which you totally can, if you do it this way, what I'm doing right now, that at least this little amount of work, you have to do. You have to at least show a little bit of something, all right? So even if you do by the inspection way, which is less work, a little bit less tedious, you still have to show some little bit, which is like just do what I'm showing you. Like, oh, this is a 2. I don't know what this is. This is 1. Okay, this must be 0 order. Okay, so we're going to just do more practice today. Now, notice this one, whoever did this experiment, they did tons of different trials. They did 1, 2, 3, 4, 5, is it 6 or 7? 6 different experiments, okay? Now, it says, oh, you know what I forgot? I lied. We didn't finish the other one. I forgot. Besides finding the reaction with respect to each reactant, we also need to find the overall order. Well, if it was second order for one of them and then 0 order for the other one, the overall order was 2, okay? Because 2 plus 0 is 2. And then we found the rate equation or the rate law. It looks like this. We had already done this. Rate equals K. It was second order with respect to X. And then because Y was 0 order, we omitted it from the rate law. So this is our rate law. Again, don't get confused. Just because Y is not written in the rate law does not mean it's not part of the chemical reaction. If you see X and Y reacting, they're still reacting. It's just that Y doesn't change the rate of the reaction, but it's still reacting chemically. It just doesn't speed up or slow down a reaction no matter how much you mess with it, okay? And then this is what we have not done yet. We have figured out how to do the units for the rate constant, but we've never figured it out mathematically with actual numbers. So that's what we're gonna do right now. So you go, well, how do I find the rate law constant, K? You get to pick any trial that you want. Any trial. Experiment 1, experiment 2, experiment 3. It doesn't matter. So I'm going to pick experiment 2. Can someone take a chance and do a different experiment for me? Anybody? Anybody want to do experiment? Will someone volunteer for number 1 and number 3? And I'll show you what to do with them. Basically, I'm going to use this data. Anybody brave enough to try a different one? Please? You'll do 3? Okay, thank you. So I've got a 3 in class. Emma, will you do 1? Thank you. So here's what you do. You pick any experiment you want, and you just plug all of that data in to the rate law, and then rearrange and solve for K. So if we go, if this is my rate law, rate equals K, concentration of X raised to the second power. I'm just going to rearrange and solve for K before I plug numbers in, okay? All right? So I'm going to move this guy over here. So it's rate over the concentration of X to the second power equals K. So I'm picking experiment 2, so I will use the rate for experiment 2, which means if you're picking experiment 1, you will use the rate for experiment 1. So my rate is this guy. If you're doing 1, this is the number you plug in. If you're doing 3, this is the number you plug in. It just doesn't matter as long as you pick one experiment and use all that data. So my number is going to be 4 for the rate. And notice that it's molarity per minute for the units. So mine is 4, my rate up top, molarity per minute. That's what the -1 means, right? Divided by the concentration of X. So I go back. I'm doing experiment 2. So my concentration of X is this number, and notice the unit is in molar, big capital M for molarity. So if you're doing experiment 1, you're going to plug in this number. If you're doing experiment 3, you're going to plug in this number. And now notice my rate law doesn't have Y, so I don't even care about anything about Y. So I'm going to plug in 0.0100 molar. let me see, hold on. I think it's 0.005. Yeah, 0.00. It's the same as 1. 1 and 3 are the same number. 0.00500. Okay. Now notice my molarity cancels. And now I'm going to get, I finally got a calculator. Are you proud of me? Okay, and then yes, look, oops. Ooh, thank you. Eek! I forgot, which is easy to do, the square, which means this is molarity squared on the bottom. It's 0.01 squared times molarity squared. So really this is 4.00 molarity per minute divided by 1 times 10 to the negative fourth. That's what 0.01 squared is. And then molarity squared, which is molarity times molarity. You've got to square the 0.01 and you've got to square the units. So I'm going to rewrite the m squared is just 2 of the m's because it means the same thing, right? M times m is m squared. And I'm only doing that so you can easier see how the units cancel. So one of the molarities cancels. Now 4 divided by 1 times 10 to the negative 4 is 40,000. Is it 3 sig figs? It is. Ugh. So I have to write this in scientific notation. 4.00, it's 40,000 times 10 to the fourth. Now my units are m minus 1, because it's in the bottom, and minutes minus 1. So this is the K constant. Now, let's see. Emma, is that what you got? You did experiment 1, right? Did you get the same exact number? Yep. You're still working. Just wait 1 second. We're still waiting on experiment number 3. 40,000, right? So the whole point is it doesn't matter which experiment you pick to solve for K, whatever one you want, all right? So K is determined by you just plug and chug one of the sets of data in and rearrange. That's all. So we're going to do a bunch more now. All right. So here's a new reaction, as we had just kind of mentioned. Ammonium and nitrite making nitrogen gas and water. It asks you to deduce, which means figure out, determine the order of the reaction with respect to each reactant, the overall order, so you add those together, the rate equation or the rate law, same thing, and then solve for K. So having said that, do you guys feel comfortable enough to do this on your own yet, to try to write a rate law, or you want to do one more together? One more together? No? Yeah, maybe? How about we'll do this one together and then I'll set you free on the next one. We'll kind of like brush back up. Now, here's the thing. There's lots of options for which experiments to pick on this because they did so many. You'll see that there are a lot of times where, like for example, look at between experiment 1 and 2, ammonium is changing and nitrite is not. But same thing with 2 and 3. Look, ammonium is changing and nitrite is not. Or look at even 1 and 3, ammonium is changing and nitrite is not. So there's many options to go about finding the rate law. And it doesn't matter who you use because if the data is correct, they should all follow the same pattern. So I'm going to do I'm going to do 1 and 2. Okay? Now I'm going to do this by inspection at this point. So here we go. So remember, a rate law looks like this. Rate equals K, and I'm trying to find the order of ammonium, and I'm trying to find the order of nitrite. These are both of my reactants. Okay, so I'm going to try to find it with respect to ammonium first. So again, I have chosen to do 1 and 2 because this guy stays the same. So I can just focus on how ammonium is changing it. So between one, this is concentration, right, which is over here. What's happening to the concentration? It's doubling, right? I'm ignoring K, right, for now. What's happening to the rate? Look at just the coefficient up front. 5.4 times what is 10.8? 2, is that right? It's doubling. So 2 to the what is 2? That's a 1, right? It's okay. So I'll write a 1 right here for just right now, but I'm gonna get rid of it in a little bit. So it's first order with respect to ammonium. And then you do it again, but you do it for nitrite. So if we want to look at nitrite, we'd like to focus on how ammonium is changing. Or I'm sorry, if we want to look at nitrite, we want to focus how nitrite is changing, ammonium is not. You have a plethora of options. 4, 5, and 6 all has ammonium staying the same concentration. So I could do 4 to 5, I could do 5 to 6, I could do 4 to 6. It doesn't matter. And in fact, I'm going to do 4 to 6 because I think kids get so stuck in doing ones that are right next to each other that you can't think out of the box. So I'm going to do 4 to 6 because ammonium stays the same concentration. So between 4 and 6, it looks like the concentration is quadrupling. 0.0202 times 4 is 0.80808. Okay, so we don't know the power. So concentration raised to the power. Now let's look at the rate. 10.8 to 43.3. What does that look like? Does that look like quadruple, approximately? So the rate is quadrupling. So 4 to the what is 4? 1. So it is first order with respect to nitrite. So overall order is 2, right? Because 1 plus 1 is 2. So I'm going to just rewrite my rate law nicely. Overall order 2, and then the last thing they ask you to write is find is the K constant. We have 6 different experiments we can choose. It doesn't even matter which one you pick. They will all give you the same rate constant. What changes the rate law constant, K? If you're doing the same experiment, assuming you're not changing the experiment that you're doing, so if you're reacting ammonium with nitrate, what is the only thing that can change the rate law constant, little k? Do you remember? Temperature. Temperature. And we'll talk more about why later. All right, so here we go. What one do you want me to throw in there? Pick any experiment you want. 1. Well, James, how boring. I'm just kidding. All right, so I'm going to rearrange this to solve for K before I plug numbers in. I'm going to rearrange the variables first. So rate divided by NH4 plus NO2 minus equals K. This is just an algebraic manipulation to get these guys on the other side. And then after this, it's just plug and chug. So LeJames picked experiment 1, so we're just going to plug all of this in. So the rate for experiment 1 that goes on the top is 5.4 times 10 to the negative 7th. Then again, the units are molarity per second divided by the concentration of ammonium for experiment 1. So 0.0100 molar. And the concentration of nitrite for experiment 1. So 0.200 molar. Now be careful in your calculator to avoid issues unless you are really good with parentheses. I would just hit 5.4 times 10 to the negative 7th, divide by 0.01, and then hit the divide button again. It helps avoid any parenthesis calculator issues. So my molarities cancel. And I don't know, I have to do this. I got 2.74 times 10 to the negative 4. M minus 1, S minus 1. Anybody else get that? Anybody doing a different experiment besides one? Or did everybody do one? All right, well, anyways, if you did a different one, if you picked experiment 3 or 5 or 6, you still should have gotten the same exact number. Okay? All right, so let's see. All right, I'm going to give you guys time to do this one. I'd like you to see if you can do this one by yourself, please. So I'll give you like a couple of minutes. So deduce means figure out the orders of each reactant, the overall order, the rate equation, and then the value and units for the rate constant. Okay, so the rate law is first order with respect to A and first order with respect to B, which means the overall order is 2 because 1 plus 1 is 2. And then to find the rate law constant, I used experiment 2. Maybe use experiment 1 or experiment 3, but again, the number should come out to be the same. I got 8,000, but because all of these are 3 sig figs, you have to write it in scientific notation. So that's 8.00 times 10 to the third. And then the units, one of our molarities will cancel, and then we still have a molarity in the bottom. So m minus 1, s minus 1. Did everybody get that? I'm human too. Sometimes I make mistakes. So this is a really, really good question that you don't use the stoichiometry of the reaction to determine anything about the rate law. You use only the data in the data table. That's a very good question. Any other questions? Okay. So having said that, when is the only time you would use the stoichiometry? So let's think about it. If I'm given a data table, I use just the info in the data table. If I'm given a mechanism where if this would have said this, right, this is like the first step, and it said slow, then you would write, it would be A to the second and B to the second, right? But that's because you'd be given a mechanism where they tell you who the slow step is, so you use the stoichiometry here because you don't have any other choice. The only other time is if they give you this reaction, and we kind of briefly mentioned this, is they give you this reaction and they tell you nothing else. They don't give you a mechanism, they don't give you a data table, and they're like, hey, write a rate law. Okay, well then you're kind of stuck and you have to. But generally that's not the case, because if you write a rate law based on a stoichiometric reaction and you use the coefficients as your exponents or your orders, you are making the big assumption that that means that reaction is one step only. And most reactions are not. Okay. So it's a very good question, and it is actually a really big misconception. So I'm glad you asked of when you use the stoichiometry and when you don't. All right, so let's talk about this now. We have been given a mechanism. So let's rewrite the rate law. I'm going to rewrite it real quick. So from the last problem, the rate law was rate.
You're not sharing the right screen.
Thank you. Equals K. And A was first order, and B was first order. And we said, okay, this is my rate law. And now what they're going to do now is they're also going to propose a mechanism. So before, we were given mechanisms and wrote rate laws. Now we're writing rate laws and going to check out mechanisms to see if they line up with what our rate law, predicted rate law is. So look at proposed mechanism 1. They're saying like, hey, could this be a mechanism that would follow this rate law? So remember, for a mechanism to work, 2 things have to happen. Your mechanism has to match your overall reaction, and your rate law has to match whatever your rate law says it is. So having said that, if you were to write a rate law based on mechanism 1, what would it be? Well, the first step is the slow step, right? So the rate law for mechanism 1 is rate equals K. That would be it for mechanism 1, right? That's what the rate law would be based on mechanism 1. Because we only have A, and our first step is our slow step, and you always write a rate law based on your slow step. So can proposed mechanism 1, well, does that work with our experimentally determined rate law? No. They don't match, right? So this isn't a possible mechanism. It doesn't make sense. It does not match our experimentally determined rate law. So now you go, okay, well, so it has to be mechanism 2, right? You know why. But now you're going to have to prove it. Why is it mechanism 2? Well, let's solve for the rate law of mechanism 2. So you find your slow step. Shoot. And based on that slow step, the rate law would be rate equals K, and you can call it K2 if you want because the slow step is step 2, times the concentration of X times the concentration of, who else is in there? B, right? Let me go back. And now what's wrong with this? You cannot leave this like this. And the reason is because why?
X is an intermediate.
X is an intermediate, and you aren't allowed to write rate laws with intermediates in them. So what do? You travel back up to the first step. And so we go back up to our first step, and we say, okay, the whole point of equilibrium is that the rate of the forward reaction equals the rate of the reverse reaction. So we can set those rate laws equal to each other, because that's what equilibrium means. So the rate law for the forward reaction would be rate equals K1 times the concentration of A. And the rate law for the reverse reaction would be just K minus 1, just means you're going backwards. And who's in there? Just X, is it right? So I get to do this because they're at equilibrium. So this is the rate law for the forward reaction. This is the rate law for the reverse reaction. And then what do? You isolate the intermediate so you can try to get rid of it. So I just move this K minus 1 over here. So that leaves me with X equaling this. So now what do? Well, instead of having my rate law have X in it, I plug what X is into the rate law. So I have rate equals K2. Now I'm replacing X with all of this stuff that I said X equals. Remember smorgasbord of K's? This whole term goes over there. And then the A also goes in there. And then don't forget, though, about your original rate law that has this guy in it. This guy's still there. B isn't an intermediate. B is a reactant, so I can leave that guy in there. And then, oh boy, does that match what our rate law was? This is what we determined our rate law to be. Yes, I realize this is a weird, funky looking K, but that's all right. So sometimes they call it K prime. So that is why mechanism 2 is the better mechanism, because it matched our experimentally determined rate law from those data tables. So now we're tying both of those concepts in together, mechanisms and rate laws, and how they need to kind of line up. Now, does this mean that the only mechanism that works is this second one proposed? Between these two, yes, but could there in everyday life be another random mechanism you could throw together? Sure. But between these two, this is the only, mechanism 2 is the only option that works that aligns with our rate law. So it's a possible mechanism. How are we doing? Okay? All right. So the first mechanism didn't work because remember you write a rate law based on the slow step. And so it was, that means it's rate equals K times the concentration of A, because this is my slow step and this is my reactant. And that's not what we said our rate law is. We said our rate law is this. From the last problem, this is the experimentally determined rate law. And based on mechanism A, this is what the rate law would be. That doesn't match what this is. B is missing from here. So this is not a possible mechanism based on what we know our rate law to be. It has to match. Does that make sense? Okay. So FRQ 1991. I would like you to take a few minutes, please. Again, this is kind of what we're ending with. We're ending with just practice FRQs over and over and over again until you hopefully feel good about this stuff. We have plenty of time. So I'm going to give a handful of minutes for this problem, and then we will come back to it. How many of you are struggling with writing the rate law? No one? You should notice something different about this problem. What is it? So you can find fluorine fairly easily. Is that right? Because there's a spot where the chlorine dioxide remains constant. What's the issue with finding chlorine? It doesn't remain constant at any point. So I want to go into this. So what do? Well, find fluorine then, and we'll go from there. So write the rate from here to here, 2.4 to 9.6 is a quadruple for fluorine. Is that right? About? I think. Okay, so the rate equals, the rate's quadrupling. The fluorine concentration is also quadrupling. Rate equals concentration raised to some power. So it is first order with respect to fluorine. Okay. So now what do? So you go, okay, it's first order with respect to fluorine. So the F2 is first order. Well, if you know it's first order, you can plug that in for it if you were to write a rate equation, right? So, for example, between experiments 1 and 2, the concentration is doubling. Now, this would be a good time to use the long way. It would be helpful because you can do it conceptually, I'll show you, but if the concentration of ClO2 is doubling, but the concentration of F2 is also doubling. Oh, sorry. Doubling and doubling. What is this guy doing? 2.4 to 9.6. Ooh, is that quadrupling? Right? So the reason you have to consider the other guy is because they're both changing. Not one of them, the other one's not remaining constant. So if this changes by a factor of 4, you have to account that part of it is because of the fluorine, right? Well, if fluorine is first order, you would have to get rid of it over here. So what you're looking at now is that just the ClO2 is doubling, and it's truly only causing a doubling on the rate because fluorine's accounted for some of it because it was also doubling in its first order. So really, the order of ClO2 is also the number 1. Again, this is harder because one of them didn't stay constant at any point. So you have to account for both. So here's the trick. There is one of them that did stay constant. Find that order first. You can find that instantly and then account for it in the next part. So if this guy doubles, chlorine doubles, or chlorine dioxide doubles, and fluorine doubles, they're both changing the rate. And we already know fluorine changes the rate in perfect proportion. So we know that if fluorine doubles, the rate doubles. We already determined that it was first order. So if fluorine doubles and ClO2 doubles and the rate quadruples, the doubling of the quadruple, part of that is from the fluorine. The other part is from the ClO2. This is a lot more complicated. Now, it isn't often tested like this anymore, where they don't keep one constant. They don't have spots where both of them are constant at a point, but it is something you do need to know just in case, because they haven't actually omitted it from the curriculum. Are there any questions on that? You rearrange, right, to solve for K. You pick any experiment you would like. So let's solve for K. Let's do experiment 3. So the rate constant is 9.6 times 10 to the negative third. Now, look at how they wrote the units on here. They wrote it in mole L minus 1. That means moles per liter, which means molarity. They just wrote it a weird way. So this means molarity per second. That's what a rate is. So molarity per second. And then again, this is algebra, right? These guys are going to come over here. I'm going to divide both sides by them. So, and that will equal K. So this divide by ClO2 concentration. Well, experiment 3 ClO2 is 0.02 molar. And the F2 is 0.2 molar. So 9.6 times 10 to the negative third divided by 0.02 divided by 0.2. Oop. What just happened? Sorry about that. And I get 2.4. Did you get 2.4? And then one of the molarities cancels, and we're left with M minus 1, S minus 1, because the molarity is in the bottom and the seconds is in the bottom. Okay. In experiment 2, what is the initial rate of decrease? Never mind. I'm going to skip that. We're going to skip that for right now. We'll come back. There's still more on this one. So, which of the following reaction mechanisms is consistent with the rate law we just developed? So let's flash back. What is the rate law we just developed? Why is this not changing? Hold on, sorry. Oh, my computer's freezing. Sorry guys, give me 1 second. So again, while this is loading, the rate law is first order with respect to ClO2 and first order with respect to F2. My screen never pops up. So you want to pick the mechanism that matches that. So you write, I'm just going to write the rate law just to refresh. So rate equals K ClO2. My gosh. That's what we determined in the prior part. So look at this first mechanism, mechanism 1. If you were to write a rate law based on mechanism 1, ooh, this is ugly. Actually, I'll skip that for just a second. Look at mechanism 2. Oh boy, what is that? I don't even know what that says. I think it says F2 for mechanism 2. Hold on. Let's go to my slides. It's kind of cut off by the screen. Yep, that's definitely an F2. So for mechanism 2, let's see. Before we go to mechanism 1, if we were to write a rate law, it would be rate equals K. My slow step is my first step, which makes writing a rate law really nice. So all we would put, there's only F2, right? So does this match what my experimentally determined rate law is? So we know it's mechanism 1. So mechanism 2 is out because they don't match. So let's try to prove, because usually when that happens, they will ask you to prove it. Like you won't just get to say pick one, they'll say justify your answer, which means you need to kind of prove that this is true. So what do? We write a rate law based on the slow step, which unfortunately is my second step. Rate equals K. Concentration of ClO2F2, this big kind of molecule. And you go, I'll call this K2 only because it's the second step, right? First step, third step. And you go, oh no, this is a intermediate. Look, it's produced and then consumed. So I can't write a rate law like that. So you go up back to the top and you set the rate laws equal to each other because you're assuming you're at equilibrium. That's shown by the two-way arrow. So the rate law for the forward reaction would be rate equals K, ClO2, F2 equals the rate going forward equals the rate going backward. Sorry, I'm kind of running out of room. And then there's that intermediate in there. You just move the K minus 1 over and then plug in. And notice it's going to match now, right? You'll have the ClO2 in there and you'll have the F2 in there. And now that mechanism is consistent with our experimentally determined rate law. All right, last one for today.